Hello everyone, this is Group 8. I'm Rao Yunheng. We're going to introduce our project, an effective and memory-efficient framework for multi-view outlier detection in data stream. And we divide the presentation into 5 parts shown in the slide. Let's move to the first part. Multi-view outlier detection and clustering of data streams are both hot topics nowadays. The stream data clustering problem becomes a concern for us because it's a prerequisite that we can deal with streaming, data summarization, and outlier detection. In addition, as the size of data stream grows, the number of outliers will also increase. It's a must for us to detect these outliers so that we can use data better. There are two types of outliers shown in the right picture. Attribute outlier is an object that is an outlier in each view, such as the green triangle. And class outliers is the object that is not continuous between the two views. For class outliers, it's difficult for them to change from outliers to inners because of their discontinuities. In addition, objects such as attribute outliers may become non-outliers with the arrival of new set of data points in data streams. Therefore, in our project, we mainly focus on attribute outliers. In our work, we propose a meaningful solution about streaming data processing, namely multi-view outlier detection in data stream. Before we start to design our algorithm, we carried out some investigation. Streaming data clustering is often more difficult than clustering regular data sets. This is because the arrival time of the data does not necessarily satisfy the uniform distribution. And with the arrival of streaming data, clusters may experience migration, extinction, and merge issues. At the very beginning, we access to some paper about the clustering algorithm. We find there are several proposed algorithms. The clustering algorithm was first proposed to solve the streaming data clustering problem, which is based on the concepts of microclusters and pyramidal time frame. However, it can only deal with special type of data. Then we find density-based algorithms such as DB-scan algorithm, but it's not suitable for high-dimensional data. Finally, we adopt affinity propagation algorithm, which is based on the information transfer between data points.
Hi, Professor and everyone. My name is Yuying Yi. As Yunheng just mentioned earlier, we identified the two problems here. One is streaming data clustering, and the other is multi-view clustering. We try to solve the problem multi-view outlier detection in data streams. Before that, I would like to introduce one of the very important paper, which firstly proposed an effective way to solve the multi-view outlier detection problem. Why do we need to apply our algorithms to multi-view? Firstly, nowadays, we use more sources of information to describe different properties of the same object. For example, we can use either a movie genre, or B, user tags to classify the same group of a movie data set from where we may or may not achieve the same conclusions. In the example of the presentation, the movie Wall-E by Jaron is expected to be liked by kids, but it is liked by grown-ups based on user reviews. Also, to find inconsistent items under different views can be very useful in many fields, including Internet of Things, intelligent transportation systems, marketing or banking, and etc. So, what's the definition of a horizontal outlier? We say if an object is assigned to different clusters when using different information sources, it is a class outlier. I will briefly introduce the idea of a horizontal anomaly detection. First, suppose we have a set of n objects and two information sources. From the two information sources, we can derive two n times n similarity matrix A and W, where Aij and Wij represent the similarity between item I and j from two information sources respectively. Let big M to be the matrix M times I, where M is a large positive number as a penalty parameter. We have Z to be the matrix of the combined matrix as shown in the presentation. Now we start to construct the algorithm. Step 1, we compute the graph Laplacian L as below. Step 2, we compute the k smallest eigenvectors of L. And then we let B to be a 2n times k matrix containing these eigenvectors as shown below. So U and V correspondent to two soft clustering representation of X with respect to A and W respectively. Step 3, compute the anomalous score for object Xi using cosine distance between the two vectors as shown below. As we can see, the higher the score Si is, the more likely Xi is a class outlier. Similarly, the algorithm can be adapted to handle more than two information sources. We can see the advantage of the algorithm is it could be very effective. However, the disadvantages are also significant. First, when n is very large, the dimension of the Laplacian matrix will become very large, which will also increase the complexity. Second, when the number of information sources increases as shown in this graph, we can see the computing time will also increase largely.
Hello, this is Zhang Wenchong speaking. In this first part, I would like to talk about the algorithm design for multi-view outlier detection in data streams. The algorithm proposed in our work can be roughly divided into 3 steps. Firstly, we store parts of the data in memory and do the multi-view cluster for the static data in memory. In most cases, the data in each cluster satisfies a normal distribution. So the cluster center is the expected value. In other words, these clusters are often convex sets in distant space. According to this feature of the cluster, we can make use of the n-sum SQ method in the BFR algorithm to represent a cluster. BFR algorithm is often used to cluster large-scale data sets. It is difficult to store all these data points in memory, so we use n-sum SQ method. This is proposed to minimize the memory occupied by this cluster. Assume that we have a cluster C, then it will be represented as in the picture shown in the page. As the memory cost is 2 multiplied dimension added by 3. Due to the additivity of n-sum SQ, we can easily update them when we get new data, which is very effective for processing the streaming data. Then secondly, every time the new data points coming in, we need to update the clusters for each view. Because as new data points arrive, clusters may migrate, may die or merge. As we mentioned earlier, we assume that the data in each cluster satisfies a normal distribution, with the cluster center as the expected value. According to the idea of density clustering and the normal distribution satisfied by each cluster, we wish that each cluster can maintain a curtain density. That is, the number of objects is the average unit space, cannot be too small. From this, we can get a function delta n with the number of objects in the cluster n as a variable to calculate the cluster radius of each cluster. In this way, when we get a new streaming data point, we can incrementally update the state of the cluster. From the picture on the right-hand side, we can see the situation about how the clusters expand, merge, and migrate.
Hello everyone, I'm Tan Yongwei. I'll talk about the remaining part of the algorithm. After clustering, we need to continuously update the clusters as the streaming data arrivals. Meanwhile, we need to design an algorithm to determine whether the object is an attribute outlier or a class outlier. Our proposed method is to construct a new distance space of d plus 1 dimension in each view. On the left-hand side, we can see a picture about how to construct a new distance space. We select d plus 1 clusters with the most d plus 1 importance from each view based on the weight of the clusters. Every time a new data point comes, for example, the yellow one in this picture, we will calculate the distance between it and the clusters in each view. Then we will get a d plus 1 dimension distance vector for each view. Actually, we have to normalize the distance vector before we use it. Now the new distance space is constructed. It's a simple but effective structure that can help us to find the class outliers easily. Now we will talk about how to detect the class outliers and attribute outliers. We know that class outlier is the object that is not continuous between the two views. So how to measure the continuity is the key. In our work, we set a value called SC to denote the possibility of a data point is a class outlier. Based on the distance space we mentioned before, we will get a vector for the data point in each view called vector 1 and vector 2, and the SC is equal to the normal of vector 1 minus vector 2. In other words, SC is the distance between V1 and V2. So the one with bigger SC will more likely to be a class outlier. And the attribute outlier is the object that far away from every clusters in each view. We set a value called SA to denote the possibility of a data point is an attribute outlier. And the process shows in the process of it is shows in the left-hand side of this page. So the one with bigger SA value will less likely to belong to any cluster in every view. Finally, we will add SC and SA value to get a value called SO. And SO can help us to detect the outliers in multi-views, no matter they are class outliers or attribute outliers.
Next, I'm Han Jiaqi, and in this section, we used a large-scale 2D dataset to simulate the arrival of streaming data, and its clustering results are different in different views. In our experiment, we consider the case of dual view. We construct a new distance space for each object. Then we select the two types of outliers and non-outliers and calculated their SO, SC, SA values respectively. SC describes the discontinuity of the object between the two views. SA is proportional to its distance from the nearest cluster. Here is our formula. This picture shows the SA values of the three types of objects. We can see that the SA value of class outlier is overall higher than that of non-outliers, but the SA values of these two objects still overlapped, which makes it difficult for us to find an accurate threshold delta C for distinguishing class outlier from non-outliers. Our solution is to introduce a penalty mechanism. This equation shows our method. This picture shows the new SA value after introducing the penalty mechanism. We can see that there is almost no overlap between the SA value of class outlier and the non-outlier. We can easily find the threshold delta C, for example, equals to 1.48 to distinguish class outliers from non-outliers. After introducing the penalty mechanism, the SA value can be used to distinguish attribute outliers from non-outliers. Obviously, for each attribute outliers, its SA value is 0, while the non-outliers SA value is always greater than 1. We can set the threshold to delta A equals to 1 when SA smaller than 1. The object is an attribute outlier. Otherwise, it's a non-outlier. In our project, we proposed an effective algorithm for multi-view outlier detection in data streams. Based on the characteristics of streaming data, we used the BFR algorithm to represent clusters, which allowed us to maximize the use of memory. We also easily detect class outliers by constructing a new distance space, which makes our algorithm efficient and able to meet the requirements of streaming data processing. In addition, our algorithm can precise every incoming data point in real time. By calculating its SA and SA values, we can even judge which type of outlier it belongs to. And that's all. Thank you.